Welcome to the continuing use of stoichiometry. I'll even bypass the space and time routine and get right into it. We're going to expand upon what we just did, which was reactant to product, and we're going to look instead of at a single reactant, what happens if we look at all the reactants? So let's go back to my awesome artistic ability. You can see 8 beautiful BMW frames here. You can see 8 beautiful white wall tires here. And if I said, and let's go back to our chemical equation, 1 car frame plus 4 tires can yield me 1 car. Now let's go back to the stoichiometry idea. And what's going on? So what happens if we start to put these things together? And you guys know this. 1 frame helps if the marker works. 1 frame will use up 4 tires. And another frame down here will use up 4 tires. We'll get 2 cars out of this. And I'll have 6 frames sitting there. Can I make more cars out of those frames? And that's a bit of a trick question if you're thinking so at home. Because the short answer is, with what I have, no, I cannot make any more cars. But if I added in more tires, I could produce more cars. And this is true with the chemicals as well. So when you put 2 chemicals together, 2 reactants together, it's really quite rare and almost impossible to have perfect amounts where they would both exactly run out at the same time. One of them is going to be left over, which we would call in excess. And one of them will disappear, which is what we're going to call the limiting reactant. Because we stopped making cars when we ran out of tires. The frames, we could make more cars. So what stops our reaction or quenches our reaction or just makes it so we can't make more of it, can't make more product, no more production, products, you get the idea, is when we run out of something. So when we run out of something, everything stops. And what we run out of is what we call the limiting reactant. It limits the reaction by running out. So this is an important concept. Theoretical yield's another one. The calculation we did in the last video was a theoretical yield. I might have used it in passing, but now I want to formally talk about that. That's at a maximum amount of product that can be expected. Again, just because we can make 2 cars out of this scenario doesn't mean someone doesn't break a tire, lose a tire, pop a tire, whatever, and then all of a sudden we can't make that second car. So just because it can happen doesn't mean it will happen, or we have to have somebody actually put the tire on. Maybe we make 0 tires. They're sitting there, but we never ever get a car. That's realistic. It's possible. And then you start talking about chemical scale where you're talking about billions and trillions and gazillions of atoms and molecules having to find each other, and you can imagine a lot of things could go wrong or on side tracks or just never find each other. So I want to take one more look at this math here. This number out front is really how fast it gets used up. So the bigger the number, the more of it we need. We need 4 times as many tires as we have frames. So if you start with a reaction like this, where you have equal amounts of frames and equal amount of tires, well, then you're going to run out of whatever you need more of, so the bigger number you run out of first. For example, 8 frames predicts making 8 cars. 8 tires predicts making 2 cars. And we're about to do this calculation for real with chemical problems here in a moment. But I want to point out which one is our realistic one. The 2 cars here or the 8 cars we make out of the frames? It's the 2. It's always the smaller number. The smaller number is the one we want. We're going to do this type of thing where we do double calculations. One of them ends up being useless, but we don't know that till we do it, so we have to do it. And the other one is the one we want. That's the important one. And it gives us 2 things. The answer is our theoretical yield, and whatever we started that calculation with is our limiting reactant. But we have to do the calculation to know which number is smaller. And again, it's the small number we want. Before we do the math, let's just look at that conceptually one last time. So let's take a more complicated reaction. Sulfur comes in little 8-membered rings, yellow smelly powder. Take our sulfur, add some fluorine, we can make sulfur hexafluoride. And it's a 1 to 24 to 8 ratio. So if I said I had equal amounts, and again moles is amount, so if I have equal amounts of sulfur and equal amounts of fluorine, which one runs out first? Good, it's that bigger number. Fluorine runs out first. Fluorine would be our limiting reactant. Now if we look at the second problem, where I have 1 mole of sulfur and 24 moles of fluorine, you can see that's the exact ratio we're supposed to have. And this is the odd case where they would both run out together and they would both be limiting reactants. If you ever had more sulfur than fluorine, if you had more than this, if you had a 25-to-1 ratio, then you would actually flip this over and you would finally have sulfur eliminate. Now, last point, and usually when we measure things and we talk about things, we actually talk about masses in grams. Grams is not directly related to the amount. Just because I have the right ratio of grams doesn't really tell me how much I have about each of these things. Sulfur is a lot heavier than fluorine. Well, SA is a lot heavier than F2. This makes a difference in that ratio. Grams tells us nothing, and I want to point this out. I don't know. I don't know. Where's the periodic table? All right. So again, moles we can compare. Masses, we're going to have to do math. What's the math look like? Wonderful question. The math starts to look something like this. Let's take a very simple reaction. We can burn calcium in the air. If we take some calcium metal, we heat it up a little bit, it'll combine with oxygen, form calcium oxide. If, for example, I did this in a closed environment and I had 20 grams of calcium and 10 grams of oxygen, what is the maximum amount of calcium oxide I can produce? So again, remember last time, our giveaways. I have a number about chemical A. I have a number related to chemical B. They asked me to calculate chemical C. There should be a neon bulb flashing in your brain going, molar-mole ratio, molar-mole ratio, molar-mole ratio, molar-mole ratio, chemical A, chemical B, molar-mole ratio. And following that light bulb flash should be someone going, we need a reaction, we need a reaction, we need a reaction. Luckily, we've been supplied a reaction. And remember what I said last time, I like to pull each piece of information out and put it in columns underneath those chemicals. So for calcium, I have 20 grams. For oxygen, I have 10 grams. For calcium oxide, I'm supposed to figure out how many grams. And then I put the formula weights here just to move us along on these videos, which you'll just get from the periodic table. Take the bigger numbers, add up the pieces. Okay. Now my question is, I have nothing about calcium oxide, which means I'm going to have to get it from somewhere else. Do I get it from the oxygen, or do I get it from the calcium? Well, the answer is kind of neither or both, depending on how you look at it. I don't know what the right one is. I'm going to have to do some math. And I can't say that I have my perfect 2-to-1 ratio for my reaction because I don't. It's grams. They weigh different amounts. We need to do a calculation. So, I'm a creature of habit, so I'm just going to start on the left. 20 grams of calcium. I need calcium. I have calcium oxide. That means I have to use a molar-mole ratio. And that means to use a molar-mole ratio, I have to get moles. Do I have a direct relationship between grams and moles? Absolutely. 40 grams per every mole of calcium. Now I have my molar-mole ratio, so we'll use it. Moles of calcium on top. Cancel it out. Moles of calcium oxide over here, since that's what I'm asked about. Now I go to the reaction. This is a 2. This is a 2. This 2 comes down, stays with calcium. This 2 comes down, stays with calcium oxide. And if you want to cancel those out, that's fine. Or you can punch them in your calculator. They want grams. Do we have a direct relationship between moles and grams? Oh yeah, we use that all the time. Formula weight. I know this one, Dr. Orgo. And there you have it. So from here, we punch through, we get a number. I know, fascinating. All right, so I get 28.0 grams of calcium oxide. This may or may not be the right answer, as I was saying. We need to do the exact same thing for oxygen. And you're going to see the similarity in the calculation, and you'll see that the numbers mean slightly different things. So same idea. We have oxygen, we want calcium oxide, we need a molar-mole ratio, we have grams, which means we're starting with our formula weight, which in this case is 32-to-1. Now we'll use our molar-mole ratio. And this is still 2, but oxygen now has a 1 in front, so we bring that 1 down. And then lastly, the formula weight's exactly the same. And just like our example with the cars, the number we want to keep is the smaller number. And in this case, I get 35.1. And hopefully, it's pretty obvious that 28 is smaller than 31. Or sorry, 35. This is the smaller number, we keep it. This is smaller, that's the one we keep. This is our theoretical yield. And the answer to the question. This, once we realize that, that means oxygen's in excess. This calculation doesn't mean anything, which is very sad, but you know, at least we get to use our calculators. And this is our limiting reactant. So we were able to get quite a bit of information from that problem. Hopefully you found this helpful. We're going to do more of these types of calculations in class, both now and moving forward throughout the semester. And thank you as always for your time, attention, energy, and positive attitude.